Welcome. Let me remind you that we were discussing supernova and how you can determine distances using supernova. So, supernova can be used to determine, supernova of type 1a can be used to as standard candles to determine luminosity distances, and these are usually represented as in terms of the distance modulus, and the different cosmological models predict the distance moduli as a function of redshift, and these come out to be different. They come out to be different, the predictions for different cosmological models. And in this picture, the difference in different distance moduli between various cosmological models with relative to this one has been plotted along the y-axis, and the redshift has been plotted along the x-axis. So, the horizontal line through the center is this model, and the upper curve, the lowermost curve, is a model which has only matter, omega matter equal to 1. And the curve over here is a model which has a mixture of matter, 0.3, omega matter is 0.3, the rest of it is curvature. And what the data shows you is that none of these three models are able to fit the supernova luminosity distances as a function of redshift. The distances come out to be larger than predicted by all three of these models, because the supernova appear to be fainter than predicted by these three models. Okay, so it is necessary to invoke a model which has a constituent with negative pressure. This is what we were discussing in the last class. Let me, so if you allow for a constituent with negative pressure, we call it lambda, and negative pressure such that the pressure is equal to minus the density into c square. Pressure, the density, the equation of state parameter is -1. If you allow such a parameter, and then you allow this, so you have a model where you have three parameters, omega matter naught, omega curvature naught, and omega lambda naught. Any two of these can be varied. The third one is determined from the fact that these sum is 1. Okay, so the different cosmological models can be, each point here represents a different cosmological model. Okay, and the solid line are the models which are spatially flat. Okay, and yeah, the region over here, the line over here demarcates the difference, the division is the division line between models which are accelerating at present and models which are deaccelerating at present. So that is the question that we were addressing at the end of last class. What decides this? So if you look at the equation that governs the evolution of the scale factor, this is the equation, and for a model which has these three parameters, this equation then becomes this. The curvature obviously does not contribute to a double dot. It is in our interpretation, it is a constant of integration that you encounter when you integrate this. There will be a factor of a here. This is the equation, which we have already encountered and integrated, hopefully familiar with us by now. Okay, so this equation predicts that the universe will deaccelerate when this term dominates. So, and it will accelerate when this term dominates. So the transition will occur at a scale factor a which is equal to 2 omega lambda naught by omega matter naught to the power minus 1/3. So this number is obviously, if this is 0.7 and this is 0.3, this number will obviously be less than 1, more than 0 but less than 1, because this ratio is more than 1. Okay. So at some redshift in the past, there was a transition, the universe underwent a transition from a phase of deaccelerated expansion to a phase of accelerated acceleration. Okay. So deaccelerated acceleration means that if I plot the scale factor as a function of time, the second derivative is positive if it is accelerated and the second derivative is negative if it is deaccelerated. So positive second derivative means like this and negative second derivative means like this. So there was a transition here, I am just drawing it pictorially, it may not be so dramatic, like this, and this is the present value a equal to 1. And once this term dominates, we know that the expansion is going to be t to the power 2/3, matter dominated. Okay. And it is, the universe is approaching exponential expansion, e to the power some constant t, right, that is if you have cosmological constant dominated, this term dominating. So we are now in a phase where we have gone over from deaccelerated expansion to accelerated expansion, that is the thing. The question is, what is this thing that is making the universe accelerate? Okay, so we shall come back to this question, that is the very important question. Let us go back to the data again. So the data seems to indicate that there is some amount of omega lambda, and the supernova data itself cannot really pinpoint what the value of omega lambda is. There are regions over here, confidence intervals, which are shown. So with 99.7% confidence we can say that the data indicates that my cosmological model should lie, our universe lies somewhere inside this region. Lesser confidence I can say that it lies within this region. This is from supernova data only. But there are other observations in cosmology which I have not mentioned. So let me show you, just show you the results from these observations. I will not go into the details of how they are determined. So these are observations of galaxy surveys. Okay, galaxy surveys map out the distribution of galaxies in space, and these observations can also be used to constrain the value of omega matter and omega lambda. In particular, they constrain the value of omega matter. They do not impose at low redshifts. These observations currently exist at low redshifts and they do not put constraints on omega matter. The observations shown over here, they constrain omega matter, not omega lambda, and they indicate that omega matter is around 0.3. Okay, and these observations are observations of peculiar velocities. We have already discussed what peculiar velocities are. So these are basically the imprint of peculiar velocities on the galaxy clustering. Okay, they indicate that omega matter is around 0.3. So these are the confidence intervals. There are also observations of the cosmic microwave background radiation anisotropies from a satellite called WMAP, which is now in orbit, even now taking data. Okay, so the cosmological parameters which are consistent with these observations lie somewhere over here. So WMAP indicates that the universe is very close to being spatially flat. This is the curve corresponding to a spatially flat universe, essentially. So WMAP indicates that our universe is very close to being spatially flat. That is the allowed parameter space from WMAP observations of the cosmic microwave background anisotropies. If you put all of them together, you are led to a model, you are led to the conclusion that our universe, the parameters for our universe lie somewhere in the overlap of all of these three, right. The universe, that the model that we choose should be consistent with all three kinds of observations, so it has to lie somewhere over here, which is around omega matter 0.3 and omega lambda naught 0.7, okay, which you see is where all of these three things overlap. So this component which has got negative pressure, this component of the universe which has got negative pressure is referred to as dark energy. Okay, is referred to as dark energy. So we have already learned about dark matter. Dark matter is something that exerts a gravitational attraction, but you do not see it. And we have discussed, for example, spiral galaxies where the rotation curve indicates the presence of dark matter. Okay. So you do not see the matter, but you see that there is something exerting a gravitational attraction, and that is given the name dark matter. Dark energy is required, is put in by hand to make the universe accelerate. So it is some constituent of the universe, again which you do not see, but it has the property that the net gravitational force acceleration is repulsive. The galaxies are actually accelerating away from us instead of being attracted to us, towards us, right. A double dot, we calculated, remember, A double dot by considering the acceleration of a galaxy relative to us, and this term lambda makes this acceleration repulsive. Okay. So this is, there is evidence that the universe has something like this, which has got negative pressure, which reverse causes gravity, the gravitational attraction, to become repulsive. Okay. Now the question, this has been given the name dark energy. Again, this is something you do not see, but so dark matter is something which has density which you do not see and pressure is 0. Dark energy is again something which you do not see, whose pressure is minus rho lambda c square. Okay, and this is required to explain the supernova data, for example. Now question is, what is this dark energy? Do we have any physical understanding? Some plausible candidates for dark energy. Well, what are the plausible candidates for dark matter, for that matter? Okay, what are the plausible candidates for dark matter? What are the plausible candidates for dark energy? Well, dark energy, there is no dearth of plausible candidates, because particle physics theories predict all kinds of particles, some of which have not been detected as yet, which also do not interact with radiation. So it is relatively easier to build models which predict all kinds of particles, massive particles, a variety of massive particles which can be candidate for dark matter. Okay. Now dark energy is something which has to have negative pressure. Massive particles which just hang around in space will be candidate for dark matter. Okay, and there are particle physics models which make such predictions. Now what the question that we are interested in here is that what is dark energy, what are the plausible candidates. So one possible candidate is the cosmological constant. The cosmological constant is a possibility that is admitted in Einstein's theory of gravity. Okay. So in Einstein's theory of gravity, curvature of space time arises due to matter, energy basically. But you can also introduce in this equation, so it is basically a relation between the curvature of space time and the matter energy density. You also have the freedom of introducing something called the cosmological constant, which is basically a constant, which is also a source for curvature. So suppose there is no matter, it is not guaranteed that my space is going to be, space time will be flat. Einstein's theory of gravity allows the possibility of there being a constant which can also make the universe, the space time curved, even in the complete absence of any matter, energy moment, any matter and energy. Okay, this is a property of the vacuum, the cosmological constant. So it is also referred to as vacuum energy. Okay, it's a property of vacuum. It's a property of vacuum, and vacuum here, so in Einstein's theory of relativity, in the Newtonian context, we believe that when there is vacuum, when there is no matter, there will be no gravitational attraction or repulsion. But in Einstein's theory of relativity, it is possible that vacuum itself may produce gravitational attraction or repulsion, which is there through the cosmological constant lambda, which you are allowed to introduce into Einstein's equations. Okay, and if you have a positive cosmological constant, then the curvature is such that it causes inertial observers to basically accelerate away from each other. And if you have a negative cosmological constant, it will cause inertial observers to move towards each other. So a positive cosmological constant will cause inertial observers who are distant inertial observers, they do nothing, they will accelerate away from one another basically. Okay, that's the property of vacuum if you have a positive cosmological constant. That is one possibility. Okay. Other possibility is that you can have scalar fields which fill our universe. Okay, that is the other possibility. They go by a variety of names, so one of them is quintessence. So you can have so basically in this situation, so here it is a constant, here the dark energy is something which is dynamical, it is a cosmological fluid. So just like you have matter spread out all over the universe, you also have another kind of fluid which is spread out all over the universe, which has got negative pressure. Okay, and such a fluid then has its own dynamics, and the scalar field is one example of such a fluid which fills the entire universe. By some means you can introduce mechanisms by which it has negative pressure. Okay, this is one possibility, and there has been considerable study, and it is still going on into different possibilities, okay. So you can change the dynamics, you can do a variety of studies here. And there is a third possibility that maybe Einstein's theory is incorrect at the length scales, at the gravitational fields that you are discussing here. Einstein's general theory of relativity is mainly tested in the solar system, and here we are applying it on scales which are much larger than the solar system. Also the gravitational forces are much weaker than those encountered in the solar system. So it is quite possible that this theory is modified, it is not applicable as it is at those length scales or at those weak accelerations. Okay, so again this is a field in which people are carrying out research direction. Okay. The point which I would like to make here is that what is dark energy is one of the biggest problems in cosmology and in physics for that matter. It is something that is still quite unknown. We know it is there, it is parameterized by one parameter omega lambda naught. As far as we are concerned, in the simplest cosmological model, we have parameterized it by a single parameter, given it a name omega lambda naught. So our entire ignorance about this has been parameterized by a parameter omega lambda naught. Okay, beyond that there is not much known, so we do not really know what it is going on. We know that the universe is accelerating, but we do not know what is causing it. On the scales of galaxies, we know that there is more matter than that you actually see, but again we do not know what it is. Okay. Now, so this is as I have tried to tell you, that this is a topic of tremendous interest in physics and in astrophysics. So there are several observational projects going on to map out this, to study this in greater detail. So let me briefly show you some of these. So there is the there are different names. So there is the Supernova Factory Cosmology project, which is aimed at probing low redshifts over here. This is one of the projects. Then there is the another project called Essence, which is using this Canada Hawaii French telescope legacy survey, and this is targeting a redshift range over here. And then there is the high redshift search using the GOODS, the GOODS survey, which is targeting here this redshift range. And finally you have this SNAP, which is targeting supernova in trying to rule out this part of the diagram. Okay. So SNAP is the supernova acceleration probe. It's a satellite which I think will be launched, as will study the dark energy of the universe. So the basic thing is that you have to measure supernova, determine supernova at with more accuracy. So you require more. The better the errors, the smaller the error bars, the better you will be able to constrain the cosmological models. Further, if you can measure out to higher redshifts, again you will be able to put better constraints on the cosmological models, and you might be able to determine what actually makes up this mysterious thing lambda. Okay, so the future is, I mean, the results are already coming from these. So this is results. These are results from the Essence, which I mentioned, and let me show you some other recent data. So the data I was showing you earlier was 2003. This is data from these are results 2010. So these are results from the Supernova Cosmological Project. This is the reference, and it's called the Union. The data that they have considered for the supernova is called the Union 2 data. It has 719 supernova 1A from 17 databases, of which 557 pass the usable cut, so 557 of them are usable. In addition, it also has 6 new high redshift supernova, and they have combined all of this data, and they are able to impose this is the region of parameter space, omega matter, omega lambda parameter space, which they are able to constrain the models to. So these again are the 68% confidence interval, the 95% confidence interval, and the 99.7% confidence interval. This is the line which corresponds to a flat universe. These are the constraints from the CMBR, and these are constraints from the baryon acoustic oscillations, things which I have not discussed. Okay, but all of these serve to constrain the allowed parameters of the cosmological parameters for our universe. Now something I should mention here, that we have been discussing very simple models where we have matter which has got no pressure, we have this dark energy which has got constant negative pressure, and we have the rest of it is in curvature. Well, these are the simplest models that you can have which has got negative pressure. You could have models where the equation of state itself changes with the redshift. For cosmological constant this will remain a constant, but if you have, for example, scalar fields, quintessence, then this W parameter itself becomes a function of redshift. Okay. So there is tremendous amount of work now going on where people are trying to determine if W is a constant, which will indicate that it is most likely a cosmological constant, or if you find variation in W, it will completely rule out the cosmological constant, indicating that there is some physical mechanism which is producing this acceleration. Okay. So let me now bring this topic to a close over here and move on to something else. Today we are going to discuss the cosmic microwave background radiation, CMBR. We have already learned about its discovery in the 1960s. This is a radiation which is nearly isotropic, and it was discovered in the 1960s, and its spectrum was very precisely measured in the 1990s, and the spectrum was found to be very well fitted by a blackbody spectrum of temperature 2.73 Kelvin. This was a satellite experiment. The satellite was called Kobe, and the experiment is called FIRAS on the satellite. Satellite was launched by NASA in the 90s, and this experiment established that this radiation which we see coming from all directions is indeed a blackbody spectrum, has a blackbody spectrum with temperature 2.73 Kelvin. This is possibly the best blackbody spectrum that has ever been measured till date anywhere, including experiments on Earth, and the error bars here have been magnified 100 times so that they can be seen. They are 1 sigma errors which are actually 100 times smaller. So this is a blackbody radiation. The peak is in the millimeter, and the bulk of the radiation is in the millimeter and centimeter range of the spectrum, and it is quite isotropic, absolutely isotropic. Okay. Now if you take a closer look, so if you remove an isotropic component, so if you remove a component of blackbody spectrum, so if you remove the radiation corresponding to a blackbody spectrum at 2.73 Kelvin and from all directions, what you have left looks like this. So there is the next thing that you see once you remove this monopole component, so the isotropic component, is a dipole which is quite visible over here. You see this part is much fainter and this part is much darker. Okay, so this is a dipole pattern. The thing that you see in the center, passing through the center, is the image, is the imprint of our own galaxy. After all, we are seeing the cosmic microwave background radiation through our own galaxy, which leaves an imprint. This can also be removed by doing observation that over a large number of frequencies. Anyway, the main point here is that after you remove the isotropic component, the next thing that you see is a dipole, and the temperature variation of this dipole is 0.0035 Kelvin, 335 Kelvin. So it is around 1% fluctuation. It is a 1% fluctuation. So it is, I said 0.1%, not even 1%. Sorry, this is a 0.1% fluctuation in the temperature. And there is a one direction in which on the sky in which the temperature is this much hotter, and another direction in the sky where the temperature is this much colder. Okay, and this dipole pattern in the cosmic microwave background radiation is interpreted in terms of our motion of our solar system. So if the solar system is moving in this is the solar system, let us say, and if the solar system is moving in some direction, then the photons from this direction with reference, so we are assuming that there is a frame of reference in which the CMBR is isotropic, and if the solar system is moving with respect to that, then the photons from this direction will be blue shifted and the photons from this direction will be red shifted due to the Doppler shift, and the shift is V by C, which is also proportional to equal. Okay, so the fractional variation in the temperature of the CMBR is directly proportional to V by C. So this is of the order of 0.1%, which straight away tells us that V is of the order of 0.001 into C, which is, and so this dipole can be interpreted in terms of our motion with reference to a cosmological frame of reference where the microwave background radiation will appear isotropic. Okay. Now if you look at, if you remove the dipole component also, so if you transform everything to a frame of reference where the CMBR, the dipole is not there, the CMBR still has some small anisotropy left. So this is a picture of the fluctuations in the cosmic microwave background radiation after you have removed the main dominant isotropic part and the dipole as well as the contribution due to our galaxy. Okay. So this is a picture of the sky, of the CMBR anisotropies in the cosmic microwave background radiation on the sky after all those things have been removed. The dominant component and the dipole both have been removed. So the fluctuations that remain, you see, are even smaller. They are of the order of 2 into 10 to the power minus 4 Kelvin. And this is an image made by a NASA satellite again called WMAP, Wilkinson Microwave Anisotropy Probe, and the satellite is still carrying out observations. This image shows you the result of 7 years of their observation. Okay, and in this image the redder parts are hotter and the bluer parts are cooler. Okay, so there are so it is, the cosmic microwave background radiation is isotropic to a very large degree. Okay, it's isotropic to a very large degree, but there are minute fluctuations in this radiation, and these minute fluctuations are very important for our understanding of the universe. Let me explain this to you without going into detail. So if you look at the distribution of galaxies in our universe, for example, I have told you that we expect the universe to be homogeneous and isotropic, at least on large scales. Now this image shows you the distribution of galaxies in a part of the universe. Each point here is a galaxy. Okay, the distance was measured using redshifts, and the redshifts are plotted along this axis. So the largest redshift that you have here is around 0.1. Okay. So it is roughly 10% of the horizon size. Okay, 10% of the horizon size, few hundred megaparsecs. Horizon is few thousand megaparsecs. And the other direction is the angle on the sky. So you have the distance from redshift and you have the angle on the sky. So what you see is that it really doesn't look homogeneous and isotropic, homogeneous at least, right? So the point is that there are large scale structures in the galaxy distribution in our universe. Okay, they are not perfectly, so there is a length scale. The length scale is somewhere around 100 megaparsecs, of the order of 100 MPC, maybe somewhat less, maybe somewhat more, beyond which the universe is homogeneous. Okay, but on smaller scales there are considerable amounts of structure, and the study of these structures is a very interesting topic itself, which we shall not go into in this course. These are referred to as large scale structures, and this is showing you the data from the Sloan Digital Sky Survey SDSS. Okay, so the question is, how do these things arise in a universe which is largely homogeneous and isotropic? So the current belief is, the belief which is also quite well established and well accepted, is that there were initially in the universe some small fluctuations in the density. It was not perfectly homogeneous and isotropic. There were small fluctuations in the density, and these small fluctuations in the density grow by the process of gravitational instability. So what is the process of gravitational instability? In this process, the regions where the matter density is slightly more than average attract the matter from other places, and the region where it is slightly below average, the matter goes out from there. And in this process, and these fluctuations grow as a consequence of that, it is an instability. And as a consequence of this process, you form galaxies. The universe in the past did not have galaxies, nothing. Okay, matter was very close to homogeneous and isotropic, but you had these small fluctuations, and the cosmic microwave background radiation is probing these small fluctuations at a redshift of around 1000. That is the basic interpretation. Okay, so the anisotropies in the cosmic microwave background radiation are probing these small fluctuations at a redshift of around 1000, and these fluctuations grow by the process of gravitational instability to form galaxies and to form this clustering pattern that you see in the galaxy distribution. This again is another redshift survey. Here again the distance is from redshift, and this is the angle in the sky. This is another redshift survey called the 2DF redshift survey, 2 degree field redshift survey. Okay, so the anisotropies in the cosmic microwave background radiation are a very important probe of how these structures formed in our universe, because they allow you to probe these same fluctuations that grow to give you this at a much earlier redshift. And the theory should be able to explain that you arrive from here to here, which it does. Okay. Another point which I should make is that the entire dynamics of this process is dominated by dark matter. So it is the dark matter which, so of the matter in the universe, the baryon, the electrons, protons, the protons and the neutrons make a very small contribution. It is mainly dark matter. So the fluctuations in the dark matter essentially which dominate the dynamics. The dark energy, it is believed, well, dark energy has negative pressure, and it is believed that the dark energy is not affected or does not participate in this process of structure formation, except for driving the expansion of the universe. That too beyond a certain, only at low redshifts, not in the at high redshifts. Okay, so this is a brief overview of the cosmic microwave background radiation, particularly what are the crucial points in the what are its crucial properties. So it is largely isotropic. There is a dipole component which we interpret in terms of our motion, and there are other anisotropies once you remove the dipole, and these anisotropies allow us to probe the large scale structure formation in the universe. Okay, now the cosmic microwave background radiation was discovered in the 1960s, and its discovery completely revolutionized our understanding of cosmology. Okay, so let me explain this to you. Okay, so we are, just imagine an observer sitting over here, and we are receiving this radiation which is in which is a black body spectrum. Now if a radiation has a black body spectrum, we know that it originates when radiation, a blackbody spectrum comes about when radiation is in thermal equilibrium with matter at some temperature T, right. So, this is something that we know. So, the Planckian spectrum corresponds to radiation in thermal equilibrium with matter. That is the picture that we have. So, we imagine a cavity at a temperature T, and if the radiation inside comes to equilibrium with the walls of the, or with the material inside the cavity, then the radiation has a third Planck spectrum or a blackbody spectrum. Okay. Now, this is the observer, we are sitting here, and we can see inside. So, if you look in the millimeter or centimeter parts of the wavelength, or even meter for that matter parts of the wavelength of the spectrum, we can see objects all the way out to a redshift of order unity and even larger. Such objects are visible. So, we can identify objects, the universe, till a redshift of order unity, which essentially tells us that the universe is transparent. Optical depth to nearly the Hubble to the horizon c by h naught. Right, you are at length scales of the order of c by h naught when you reach a redshift of 1. So, the universe, the optical depth all the way to a redshift of order of length scale of order c by h naught is less than 1, because we can see objects over here. If the optical depth was more than 1, the light from those objects would be obscured. So, we can see astronomical objects all the way out here, which tells us that the universe is transparent all the way to this distance. So, the CMBR photons that we are receiving did not, the fact that the optical depth is 1 tells us that the CMBR photons that we are receiving did not interact with matter within a length scale of the order of c by h naught. There was no interaction. If there was no interaction, how did it come to equilibrium? Right. So, this basically tells us that the CMBR that we are seeing did not originate in the nearby universe. The photons, so the CMBR photons that we are seeing because these photons have been propagating freely for nearly the horizon, nearly, not exactly, but length scales comparable to the horizon all the way out to redshift of order unity and larger, okay, 3, 4, 5, 6, till where you can see discrete objects. Okay. So, where did the CMBR photons originate? Where were these photons in thermal equilibrium with matter? So, the picture is that if you go back to high redshifts, so if you go to z much greater than 1 or a much scale factor much less than 1, we have seen that the density of matter at those redshifts will be equal to the rho naught, rho matter naught into a to the power minus 3, because rho into a cube is a constant for matter. Okay. So, the matter density in the high redshift universe was much larger. The radiation density, okay, or the temperature of the radiation, we have briefly discussed this, we shall discuss it again, also scales as the present temperature by A. So, in the high redshift universe, the density of material was much larger. The temperature of the CMBR, if you just take this, temperature is proportional to temperature into scale factor is a constant, which we have seen by looking at the energy density. We know that the energy density scales as rho r naught a minus 4, this we have worked out, and we also know that this is equal to ab t to the power 4, right. So from these arguments you can, it is quite clear that the temperature will into the scale factor is a constant. So in the early universe, in these parts in the early universe, the temperature of the CMBR was much hotter and the density was much larger. So sufficiently back in the past, the CMBR, the universe was hot and dense, and the CMBR was in thermal equilibrium with the matter at some high redshift. Okay, so this is the basic picture. So the CMBR was in equilibrium with matter at some high redshift, where the density was much more and the temperature was much higher. Further, if you go back sufficiently into the past, the temperature will at some stage be of the order of 1 MeV. We know that, so I have told you that the temperature increases as inverse of the scale factor. So if you go sufficiently back in the past, the temperature will become of the order of 1 MeV. This is adequate, this is comparable to nuclear binding energy. So all the nuclei will get disassociated, okay, and so essentially you have the nuclear reactions taking place at those high redshifts, and so you can explain the abundances of light elements, light element abundances, assuming that they were formed in this high density and high temperature material that was there in the universe at high redshifts. Okay, so you can also have nucleosynthesis of light elements. Okay, the heavier elements were made in stars, we have already learned about that. And the nucleosynthesis, the abundance of light elements are found to be more or less the same all through the universe. So this is a natural explanation for that. Now what is the significance? Why is the CMBR so important? Now that we have this basic picture, let us go back to our discussion of the CMBR. So I have told you that the CMBR was discovered in 1960s, and at that time there were two models which were competing in cosmology. One was the evolving universe, which is the model that we have been discussing. So in this model things change with the scale factor. So for example, the matter density is equal to the present matter density a to the power minus 3, etc. Everything evolves with the expansion of the universe. Okay, there was another model at that time which was also competing with this model, which is the steady state model. In the steady state model, there is no singularity in the past. The density of the universe remains a constant. So the universe expands in this model also, that is an observed fact. Both of these models have an expanding universe, but in the steady state model you have to have matter being created so that the density remains constant. Okay, so nothing evolves in this model. On the average, the universe always looks the same as it does now, and the scale factor has an exponential, will have an exponential expansion. There is no singularity. If you have an exponential expansion, the Hubble parameter also remains constant. Here the Hubble parameter is a function of time. It was larger in the past. Okay, in the steady state model you have an exponential expansion where nothing, it's like our cosmological constant dominated model where you have an exponential expansion, the Hubble parameter remains fixed. The universe looks the same all the time. Now you see, if the universe looks